In the spring of 1946, with the war barely a year behind, a man in Traverse City, Michigan, hired an aeronautics engineer and put him to work. The problem was a helicopter rotor blade. It had compound curved surfaces, airfoil shapes that changed profile from root to tip, and the tolerances were unforgiving because a blade that flexes unevenly is a helicopter that shakes itself to pieces. The standard method for cutting those shapes relied on skilled machinists working from hand-drawn templates. 17 reference points along a contour. The machinist traced the template, guided the cutter by hand and eye, and filled in the shape between those 17 points through judgment and experience. If the template was off by a few thousandths, the blade was off by a few thousandths. If the machinist's hand drifted, the blade drifted. That man was John T. Parsons, one of the most important inventors of the 20th century that almost nobody has heard of. Parsons was born January 7, 1913, in Detroit. His father ran a manufacturing business. The son never earned a college degree. He started on a factory floor at 14, and by the time the war ended, he was running his own company in Traverse City, Michigan, building helicopter rotor blades for Sikorsky. The war had taught him everything about production under pressure. The peace had given him a problem nobody else was working on. In April 1946, he hired an engineer named Frank Stulin away from the propeller lab at Wright-Patterson Air Force Base. Stulin understood the aerodynamics of the blade problem, and together, using an IBM 602A multiplying punch, a desk-sized electromechanical calculator that could multiply two numbers and punch the result onto a card, they began computing airfoil coordinates to a density nobody had attempted. Not 17 points along a contour. 200. The holes would be drilled so close together that they overlapped, and the resulting surface would approximate any mathematically defined curve without a machinist ever tracing a template. Welcome back to Trade Archive. Give the video a like, subscribe, and watch until the end for the full story. Because what happens next will change the course of machining forever. Parsons saw what this meant before anyone else did. If you could define a shape as a set of numbers, and if a machine could read those numbers and move to the corresponding positions automatically, then the precision would live in the mathematics, not in the machinist's hands. The skill would transfer from the man to the machine. That was numerical control. Late in 1948, an Air Force evaluation team visited the Parsons plant in Traverse City. They watched the punched card positioning technique in action and recognized the potential. The following year, Parsons proposed bringing in MIT's Servomechanisms laboratory to develop the real-time servo control system that would close the loop, making the machine respond to the coded instructions on the fly rather than stopping at each position. The Air Force agreed to fund the collaboration, and Parsons signed MIT as a subcontractor. What happened next was a technical triumph and a personal catastrophe. MIT's team, working under the laboratory that Gordon S. Brown had built into one of the premier controls research groups in the country, did not merely refine Parsons's idea. They transformed it. Parsons had envisioned point-to-point positioning, the cutter plunging at discrete coordinates like the drilled holes in his rotor blade templates. MIT built continuous path 3-axis contouring, a system in which servomotors drove the machine's lead screws along smooth, mathematically interpolated paths. The cutter could trace any surface that could be described by an equation. It was the difference between connect the dots and freehand drawing, except the freehand was governed by calculus running on vacuum tubes. The Air Force recognized that MIT's version was far more powerful than what Parsons had proposed. They renegotiated the contract directly with the university. Parsons, the man who had conceived the idea, funded the early experiments, and brought MIT into the project, was cut out. His subcontractor had become the prime contractor, and the inventor became a footnote in his own story. MIT acquired a surplus Cincinnati Hydro-Tel vertical spindle milling machine, stripped its manual controls, and fitted 3 independent servo-driven axes. The controller filled a room. Roughly 250 vacuum tubes and 175 relays translated patterns of holes punched across a strip of paper tape into electrical signals. A tape reader scanned the holes. The controller computed the interpolated path. The servo motors moved. The cutter followed. No hands on the wheels, no eyes on the dials. The intelligence was in the numbers. On September 15, 1952, the machine was demonstrated publicly for the first time. The audience was small and technical. Air Force officers, engineers from aircraft companies, and representatives from the machine tool builders who would have to decide, within the next few years, whether this technology was a curiosity or a revolution. They stood in the lab and watched a modified milling machine cut complex three-dimensional shapes from a block of aluminum under the sole direction of coated tape. Unmanned. The machine moved through its program with a smoothness that looked rehearsed, because in a sense it was. The intelligence had been punched into the tape days earlier. The machine was simply reading its instructions and obeying them, the way a player piano reads a roll, except this instrument was cutting metal to tolerances measured in thousandths of an inch. The room was quiet except for the hum of the servos and the sound of the cutter peeling aluminum. What they were watching was the most important development in manufacturing since the assembly line. A few of them knew it. Most of them did not yet understand what it would replace. Parsons filed his patent on May 5, 1952, 4 months before the demonstration. It was not granted until January 14, 1958. Motor-controlled apparatus for positioning machine tool. Patent number 2,820,187. Bendix took an initial license in 1955 and eventually bought all rights. The revolution. Parsons had started now belonged to corporations and universities and defense contractors. The recognition came, but it came late and it came slowly. The Numerical Control Society gave him its first Jacquard Award in 1968, 16 years after the demonstration. The Society of Manufacturing Engineers named him the father of the Second Industrial Revolution in 1975. He and Stulin received the National Medal of Technology in 1985. The National Inventors Hall of Fame inducted him in 1993. He died in Traverse City on April 18, 2007, at the age of 93, in the same town where he had first seen what the numbers could do. He had never needed a college degree to see something that entire university departments had missed. The mill was the first major builder to act on what Parsons and MIT had proven. In 1955, Cincinnati Milling Machine won a U.S. Air Force contract for numerically controlled machines capable of producing intricate aircraft parts at high speed. It was, after all, a Cincinnati Hydro-Tel that MIT had modified for the original demonstration. The company understood the implications faster than its competitors and built its own controls division under the brand name Achromatic. The first commercial numerical control machines from Cincinnati shipped in 1959. By 1966, a new generation of achromatic controls had replaced vacuum tubes with miniaturized integrated circuits. The machines were faster, more reliable, and they could be operated by workers who had never served an apprenticeship. That last detail mattered more than anyone wanted to admit. Numerical control did not just automate the cutting. It shifted the skill from the machinist's hands to the programmer's desk. The machine tool industry was building the technology that would eventually hollow out the workforce it depended on. But in the 1960s, that consequence was still decades away, and the immediate promise was too powerful to resist. Numerical control, or NC though, only automated one machine at a time. A milling machine with numerical control was still just a milling machine. The parts still had to be moved to a drill press, then to a boring mill, then to a tapping head, each transfer burning time and shifting tolerances. One company in Milwaukee was about to eliminate that problem entirely. Francis J. Trecker, the son of Edward Trecker, studied engineering at Cornell, worked at Pratt & Whitney Aircraft, and spent 2 years in Washington on defense subcontracting before returning to the family business with a conviction that would define the next 4 decades of its life. When he became president in 1947, Kearney and Trecker was riding the reputation it had earned as one of the 3 largest milling machine builders in the country. Francis could have coasted. He did the opposite. He centralized all controls research at the main plant in West Allis. He increased research and development spending dramatically at a time when most builders were cutting budgets to survive the post-war surplus slump. In 1950, the company began producing numerical control profilers and skin mills for the aircraft industry. Then, in 1956, Trecker made the decision that turned a milling machine company into the company that invented a new category of manufacturing. He recruited a man named Wallace Brainerd from Hughes Aircraft. Brainerd's career before Milwaukee reads like a screenplay somebody would reject for being too improbable. He had started in Hollywood in the 1930s, building electro-hydraulic servo systems for synchronized multi-camera shoots. The studios needed cameras that could pan, tilt, zoom, and track in perfect unison, frame by frame, across multiple rigs, filming the same scene from different angles. The control problem was identical to what machine tools would need a generation later: closed-loop feedback, sub-second response, and precise coordination of multiple axes of motion. Brainerd solved it for the film industry and then left for aircraft. He worked at Vultee, then Northrop, then Hughes, where he developed tracer controls and a numerical control parts production line for aerospace components. He understood servo systems the way a concert pianist understands a keyboard, not as theory, as feel. Trecker brought him to Milwaukee as Director of Technical Operations and gave him a single mandate: build a machine that can perform multiple metal cutting operations in one setup under full numerical control, without a human operator changing the tools. Brainerd assembled a team. The problem they solved was not milling, or drilling, or boring, or tapping. Other machines could do each of those. The problem was the time between operations. Every time a machinist stopped a machine to unbolt one tool and clamp another, every time a workpiece was unfixtured and moved to a different machine, the clock ran and the tolerances shifted. Setup time was the silent tax on every part that required more than one operation. It could take hours, sometimes days. The cost was not just labor, it was precision lost in transit. Brainerd's solution was the automatic tool changer. A rotating magazine held a selection of cutting tools. When the program called for a different tool, a double grip arm engaged both the tool in the magazine and the tool in the spindle simultaneously, withdrew them, rotated 180 degrees, and inserted each into the other's position. The exchange took seconds. The machine never stopped. The workpiece never moved. The Milwaukee Matic II was introduced in 1958 and first sold in 1959. It could mill, drill, bore, ream, and tap in a single setup under full numerical control. The industry needed a name for this new class of machine, and the name it settled on was Machining Center. Kearney and Trecker produced a demonstration film for prospective buyers. The title was 2 words long: Months to Minutes. A part that previously required fixturing and transfer across 4 or 5 separate machines could now be loaded once and machined complete. The sales figures come from the federal court record in Kearney and Trecker versus Giddings and Lewis, and they tell the story as clearly as any narrative. Sales increased every year through 1967, when annual volume exceeded $36 million. Total sales surpassed $150 million through March 1968. Over 925 units were sold at prices ranging from $90,000 to more than $350,000, an average of roughly $180,000 per machine. Brainerd's patent, number 3,052,011, for a machine tool with a mechanical cutting tool changer, was filed June 27, 1958, and granted September 4, 1962. Federal courts later called his pre-selection and simultaneous exchange mechanism a major technological advance. He had come from building movie cameras to building the machine that made modern manufacturing possible. Brainard died in 1976. Francis Trecker passed in 1987 and was elected to the Machine Tool Hall of Fame in 1994. The Milwaukee-Matic was the crown jewel, but it was not the only masterpiece the Midwest produced in these years. 90 miles north of Cincinnati, in Sydney, Ohio, Monarch Machine Tool had introduced a lathe in 1939 that would become the most revered precision machine tool of the 20th century, the Monarch 10EE. Despite the name, it swung 12 inches over the bed and held 20 inches between centers. What separated it from every other lathe on Earth was the drive. The entire power system was sealed inside a massive one-piece cast iron base, isolating the headstock spindle from every source of vibration. A flat feed belt replaced the gear trains that other lathes used, eliminating the periodic impulses that left tiny witness marks on the workpiece surface. And the heart of the machine was a variable speed direct current motor that delivered stepless speed control through the full range, from barely turning to several thousand revolutions per minute without a single gear change. The operator turned a dial. The speed changed. The surface finish was flawless. A machinist running a 10EE for the first time notices something immediately: the absence. No gear whine, no belt slap, no periodic vibration coming up through the ways. The machine is quiet in a way that feels wrong until you realize it is the sound of everything being exactly right. The base price in 1946 was $4,194. It was never a price point machine. The buyers were aerospace companies, defense contractors, government research shops, and toolroom operations where the tolerance was measured in 10,000ths of an inch, and the cost of the machine was irrelevant next to the cost of scrapping the work. If you have been watching Trade Archive for any length of time, you know this lathe. You may own one. The machinists who run 10EEs do not trade them. They do not upgrade. They hold on to them the way a violinist holds onto a Stradivarius, because nothing built since replicates what this machine does at the tolerances it holds, and they know it. The Midwest had never been more inventive. Parsons had conceived numerical control. MIT had proven it. Cincinnati had commercialized it. Kearney and Trecker had built the machining center. Monarch had built the finest precision lathe. De Vlieg's microbore adjustable boring tool, patented in 1946, could dial to a tenth of a thousandth of an inch, and his jig mill was selling steadily to every aircraft plant in the country. The American machine tool industry owned the future, and then it started walking away from itself. The pivot began earlier than most people realize. In 1943, at the absolute peak of wartime production, Frederick V. Geyer convened a diversification committee inside Cincinnati milling machine. The timing deserves to land. The factory floors were running around the clock. The company was building machines faster than at any point in its history. And the man running it gathered his senior executives and asked them to plan for a future in which milling machines would not be enough. The committee set 4 post-war goals: extend overseas manufacturing, broaden the machinery product line beyond milling, enter the industrial consumables market, develop new technologies unrelated to machine tools. Each goal was a rational response to the boom-bust cycle that had nearly killed the company twice. Together, they described a company that was preparing to become something other than what it was. The first moves were quiet. A public stock offering in 1946 raised $3.8 million. An acquisition of the chemical company Carlyle Corporation followed in 1948, bringing chemical expertise in-house. Out of the wartime metal cutting research came Simcool, a synthetic cutting fluid that became one of the company's most recognized products. In 1955, the mill acquired Heald Machine Company. In 1957, a reinforced plastics division called Simastra was launched. Each step took the company further from the milling machines that had made its name. By the mid-1960s, the trajectory was unmistakable. The company built its first plastics injection molding machine in 1968. It acquired an Austrian extrusion company in 1969. The mill was now a manufacturer of plastics machinery, chemical products, and industrial controls that also happened to build milling machines. The center of gravity had shifted. On May 1, 1970, the board voted to make it official. Cincinnati Milling Machine Company became Cincinnati Millicron. The new name was coined from mill, a unit of precision measurement, and the Greek word akron, meaning highest. The press release said it represented the company's commitment to precision across multiple industries. The employees still called it the mill, but the words milling machine were gone from the door. The name that Frederick A. Geyer had given the company in 1889, the name that had won a gold medal in Paris in 1900, the name that had been stamped on one of every 12 machine tools built in America during the war, was retired. In its place was a word that nobody outside the company could define, chosen precisely because it did not tie the company to any single product. That was the point. And that was the problem. Frederick V. Geyer retired as chairman of the executive committee in 1976. His cousin Philip O. Geyer Jr. stepped down alongside him. The third generation, James A. D. Geyer, took the chairman's seat. By 1977, Cincinnati Millicron was the largest American manufacturer of plastics machinery. It was building industrial robots. The company that 3 generations of Geyers had built into the dominant force in American machine tools was, by every meaningful measure, no longer a machine tool company. The Geyers were not alone. Across the industry, the same pattern was playing out. On March 1, 1968, the Textron Corporation acquired Bridgeport Machines. Forbes would later call it an early victim of conglomeration. Textron was a conglomerate that already owned Bell Helicopter and consumer finance operations. It added Bridgeport's profitable machine tool business, the way a portfolio manager adds a stock. The underlying logic was financial, not mechanical. Bridgeport made money. Textron wanted the money. What the machine was, what it meant, who built it, and who depended on it were not part of the calculation. Wall Street's thesis was simple: growth through acquisition, diversification as a hedge against the boom and bust cycle that had always punished machine tool builders. And the thesis arrived at the exact moment the founding families were most vulnerable to it. The men who had started these companies were gone. Their sons and grandsons faced a choice their grandfathers never had to make: run the business in an industry that could swing 90% in a single year, or sell to a corporation offering a price that made the decision easy. The larger wave of leveraged buyouts was still a decade away, but the pattern was already set. The machine tool industry had always run on the assumption that the people who owned the companies understood the machines. That assumption was breaking. And while the Americans were renaming their companies and selling to conglomerates, something was happening on the other side of the Pacific that nobody in the Midwest was watching. In 1956, a young engineer named Seiwemon Inaba, working inside a project team at the Japanese electronics company Fujitsu, developed Japan's first private sector numerical control system. Inaba had been born in 1925 in Ibaraki Prefecture, graduated from the University of Tokyo's engineering program in September 1946, and joined Fujitsu 2 months later. He was 31 years old when he built that first numerical control. 2 years later, in 1958, the team shipped its first commercial numerical control to Makino Milling Machine Company. The brand name they used was Fanuc. 4 years after the MIT demonstration. The same year, Cincinnati shipped its first commercial numerical control machines. And in a small division of a Japanese electronics company, a man who had been 10 years old when the Midwest machine tool belt was at its golden age peak, was building the control system that would eventually dominate the world. Fanuc became independent from Fujitsu in 1972. Inaba became its president in 1975. By that time, Fanuc controlled roughly 80% of Japan's domestic numerical control market and was on its way to capturing half the global market. But none of this was visible from Cincinnati in 1958. Nobody was watching. They should have been. Between 1955 and 1960, Japanese machine tool production rose by a factor of 15. In 1960, American Machinist magazine noted that Japanese machines for the first time appeared to merit recognition as competitive with the most advanced industrial nations. Between 1964 and 1967, Japanese machine tool exports to the United States rose over 1,200%. The Japanese government, through the Ministry of International Trade and Industry, was running a coordinated buildup. Low-interest development bank loans, antitrust exemptions that let builders share technology and rationalize production, a 1956 machinery industry promotion law that channeled resources into the sector systematically. The strategy was stated openly: build world-class machine tool capacity, because machine tools are the machines that make everything else. And then, in 1974, a Japanese builder did something that should have changed everything. Teruyuki Yamazaki, president of Yamazaki Mazak, chose Florence, Kentucky for his company's first manufacturing plant outside Japan. Florence sat 18 minutes from the Cincinnati airport. It was, by any measure, in the backyard of the machine tool capital of the world. The company had operated a U.S. sales office on Long Island since 1968, but Florence was not sales. Florence was production. A Japanese company was going to build machine tools on the doorstep of the industry that had invented them. Yamazaki's reasoning cut to the bone. A machine tool company has to be close to the markets it serves to understand the manufacturing culture. He picked Florence because the workforce was trained, because the supply chain already existed, and because the customers were within driving distance. He picked it because a century of American builders had made it the best place on earth to build machine tools, and now a Japanese company was going to prove him right. That Florence plant would expand 20 times over the following decades, growing to nearly 1 million square feet, producing more than 70 models. The Americans had built the perfect ecosystem. They just were not going to be the ones who kept it. The Midwest had just spent 30 years inventing numerical control, the machining center, computer-guided precision, and the finest lathe on earth. In those same 30 years, it had renamed its greatest company, sold its most iconic brand to a conglomerate, and failed to notice that a country with no machine tool exports in 1955 was on track to lead the world. Because invention alone does not protect an industry. What protects an industry is the will to stay in the room, to keep building, to treat the work as something more than a line item in a portfolio. The Japanese understood this. The Germans, who were building their own machine tool renaissance at the same time, understood it too. The Americans understood it once. Whether they still did was about to be tested in the most brutal way imaginable. Because the Japanese machines were coming. They were cheaper. They were faster to deliver. And they were good. And behind them, a wave of leveraged buyouts and corporate raids was gathering that would hit the Midwest machine tool industry with a force that made the post-war slump look like a slow afternoon.